Hello, Foenix friends. If anyone somehow got to this video from someplace other than the Foenix Discord and is wondering what a C256 Foenix GenX is, there's a link to the Foenix Systems homepage in the video description. But in short, the GenX is a retro-style computer with, at latest count, 6 different flavors of sound chip on board. And in this video, I'm going to introduce the project I've been working on, in the emulator, that will be an application for making music with all of those sound chips. Now, you might be thinking, isn't there already a tracker for the Foenix Systems? And there is. And although I haven't tried it firsthand, from the demo video it looks like it's very well made. I'll put a link to this video in the description, of course. So why would I want to write another music application? Well, trackers are very useful, are basically standard for chiptunes, and are probably what a lot of people will want to use. But for me, powerful though they may be, a tracker-style interface just wouldn't be my first choice of working method for making music. Coming from a classical background, my first choice would be pencil and staff paper. By the way, you can hear all this music on my other channel. Link in the description, shameless plug. But that won't drive any sound chips, so the next best thing would be my second favorite working method, this app called StaffPad. StaffPad is great. For a long time, it was only for Microsoft Surface, and now I think there's an iOS version. Basically, you can draw in the music notation just as you would on paper. And it even sounds great with its library of sampled orchestral instruments in a proprietary format. When I was making my only soundtrack so far for a commercially released game, a puzzle game called Chromatic Fantasy, link in the description, shameless plug, I'd say 70% of the sounds came right from StaffPad. But this won't drive any sound chips either, because, and this is my biggest criticism of StaffPad, it won't output MIDI during playback. What you can do is, when you're done composing, you can export a MIDI file and open it in a DAW of your choice for further editing. And that brings me to my third favorite working method, and the point of this project: any modern sequencer with a good staff view. The one you're seeing on screen now is Cakewalk, but there are other good ones. Now, with this DAW-based working method, you can send your MIDI playback to external devices like these classic 90s MIDI tone generators here. Notice that some of them have controls and displays that can be used to select patches and modify parameters. But even the ones that don't have the front panel interface can still have all their parameters adjusted, you just need to send the correct MIDI commands. In the chiptune realm, there are a number of solutions for getting a MIDI sequencer to control classic chips, and the one I happen to own is this device called a TeensyBoy, made by someone calling themselves Catskull Electronics. Link in the description, and this plug isn't shameless because I like this person's work and want to support them. The TeensyBoy lets you send MIDI data into a game link cable of a Game Boy. A cartridge called MGB, which is sold with the TeensyBoy, gives you front panel controls over things like which waveform to use on which channel, the envelopes, etc. But again, you don't have to control all that using the Game Boy. You can actually modify any of it by sending the right MIDI commands. For example, MGB maps controller 1 data to the pulse width of the square wave for that channel. And that is what the software I'm creating for the GenX is meant to do. It allows the GenX to act as a receiver of MIDI signals. It routes MIDI commands to whichever sound chips you choose, and allows you to assign which parameters of each chip are affected by which kinds of MIDI messages, if any. It's meant to be used in conjunction with a sequencer on a different system, probably your modern computer. With that in mind, let's take a look. This is the welcome page. We've got the Foenix stripes here, recolored with my livery, so to speak. It's just the same colors as my forum icon and part of my website. Okay, work in progress, untitled MIDI receiver project, which conveniently abbreviates to WIPUMIDERP, so definitely be picking a different title at some point, for the C256 GenX. Thank you, Stephanie, for making these machines for us. By me, with help from all of you, and thank you all again for all your help over these past few months on the Discord. And then below, there's a summary of the basic keyboard controls, which I'll go through now. The mouse is turned off for this software. All the controls are with the keyboard. So across the top, there's a row of tabs, and there's basically one for each chip. We can use these keys to move back and forth through the tabs. In keeping with the retro rainbow theming, each type of chip has a different color associated with it. The 2 soft PSGs are together in one tab, then the SN76489, the 2 software SIDs, then the 2 hardware SIDs, and then the Yamaha chips, the 2151, the 2612, and the F262. So you may have noticed that only 2 of those have any data on them, so let's head back to the soft SIDs. Under each tab, there are generally going to be pages for each voice in that chip, and you move between them with these keys. In each SID tab, we have pages for voices 1, 2, and 3, and then a page with some global parameters. Within each page, we can use the arrow keys to navigate, and the number keys with a few letter keys to type in values. The top line on each voice page is the MIDI channel on which that voice receives notes. Let's assign this soft SID 1, voice 1, to channel 0. Navigating down to the next line, we can pick the waveform for this voice. Notice, for every line, there is also an on-screen help display in the bottom area here, to remind you of things like which values are valid and what they mean, etc. Now, since a lot of us are from GenX or older, we're well accustomed to using a computer with the print manual open on the desk next to it. But I figured it would be nice, since the GenX has all of this extra memory space, to just put a lot of that kind of information on screen. Especially since there are so many chips, you'd have to have like 6 different manuals open to remember it all. This help text is showing us the meaning of the number assigned to the SID's waveform choices. I'll type in 2 for now, which is a sawtooth waveform. Now, I could have made separate checkboxes with little pictures of each waveform next to them, but it's important to represent this choice as a single number, because you have the option in this software to choose a waveform over MIDI by sending that number as a MIDI controller message. We can set that up by going over to the MIDI columns and choosing a channel and a controller number. Now, you don't have to have this channel be the same one that the voice is receiving notes on. There aren't a lot of cases in which you'd want to do that, but there are a handful of scenarios where separating channels like that becomes useful. For example, if you're making so-called process music and are keeping your algorithmic processes on their own channels. But for now, let's also assign this to channel 0. And since the parameter is waveform shape, we'll use one of the generic sound generation controllers that isn't assigned to anything specific in the MIDI spec, like controller 70. Now if we use our DAW or sequencer to send a MIDI message on channel 0 that sets controller 70 to, let's say, the value 8, the waveform for this voice would switch in real time from 2, sawtooth, to 8, noise. That's the basic premise of this whole software. You can assign just about any MIDI message to control just about any parameter on any of these sound chips. Or you will be able to once I finish it all. So, a lot more work to do. If you were hoping for a short video, this is the place to end. The rest is just details. If you stick around, we'll continue by looking at some of the features I've managed to code in already. By the way, I should take a moment to point out that this is my first time ever programming a GUI, retro or otherwise. In all of my decades of programming, it's always been with text interfaces, or I guess MIDI interfaces. Now, once I get the actual hardware, I can begin working on the MIDI handling part of this. Yeah, before anyone gets too excited, this software doesn't make any sound yet, since I don't have any Foenix hardware to work with yet. That's okay, because I wanted to focus on the GUI first anyway. I do have a GenX on pre-order, so Godspeed, Stephanie. But yeah, while this may seem backwards, the MIDI handling part of the code should be easier, since I've been working with MIDI in binary for over 2 decades now. So yeah, it's the GUI that was quite daunting, since basic things like moving the cursor around the screen, or getting the backspace key to function as you'd expect, or even just justifying these number fields. Probably super basic things for a lot of people, but it was all new to me. So then, moving down the page, when you think about the sustain level part of the ADSR envelope, it really controls the volume of each individual note, as different from the master volume control over on the global page, which controls the entire sound output for the chip. And one way in MIDI that you can control individual note amplitudes is with individual note velocity. So rather than assigning the SID's sustain level parameter to a controller number, let's assign it to key velocity by moving to the controller column and pressing the V key. Unlike the other controllers, which can be on any channel, the velocity information in MIDI is sent inside each note on message, so it only makes sense for the note on info and velocity info to be set to the same channel. That's why, when I press Enter to confirm my choice of velocity here, the channel column is automatically set to the same channel that this voice is receiving notes on. All MIDI CCs, and velocity as well for that matter, have 7-bit values, for a range of 0 through 127. But some registers in the SID are larger, like filter cutoff, which is 11 bits, or pulse width duty cycle, which is 12 bits. In those cases, we can use two MIDI controllers together, one for the coarse and one for fine adjustment. And while it may be unintuitive, these don't have to be on the same channels as the notes. In fact, they don't even have to be on the same channel as each other. Now, the MIDI spec does include a type of message that holds values larger than 7 bits. Well, several actually, but I'm thinking specifically of the pitch bend type message, which can transmit up to 14-bit values. When you assign one of these larger values to a pitch bend by pressing P while in the controller column, then when you hit enter to confirm that choice, it sets both the coarse and the fine to pitch bend, since they're now working together, and it also sets them to the same channel as each other. And in the spirit of the GenX, where you're given the tools to do whatever you want, and it's up to each user to make sense of it, pitch bend isn't just for larger values. You could assign pitch bend to any parameter if you, for some reason, really want to. Just a few more things to show. I should explain the rightmost columns here, tentatively labeled D for distribution. Most of these, as you can see, have a default value of E for exact, and that means that the value received in the MIDI controller message is exactly the value sent to the chip's register. For example, if I want to set attack length to 250 milliseconds, then I'd need to send a MIDI controller message of 9. But what if you're using a keyboard that has programmable knobs, sliders, wheels, maybe a pedal? For example, I might want to program this slider to control the attack length parameter. On this programmable MIDI keyboard, I can program this slider to output on whatever MIDI controller number I want, and I can use this software to map that controller to this voice's attack length. But the problem is that only values 0 through 15 are valid, and those are all going to be in a very small range at the very bottom end of this slider. To solve this, I can use the software to set this parameter to spread mode by hitting the Enter key here in the distribution column. This spreads the 16 values out evenly over the entire 0 through 127 range of the slider. Even the on-screen help area updates to reflect this. In exact mode, only a 9 will result in 250 milliseconds, while in spread mode, any controller input value between 72 and 79 results in 250 milliseconds. Spread mode is especially important when assigning anything to velocity. In fact, when you confirm an assignment of velocity to any parameter, it automatically changes the distribution mode to spread mode. I mean, if the parameter only has values up to 15, then those would have to be very soft key presses. Then again, maybe you're not playing a keyboard or using it for data entry. Maybe you are programming individual velocities right in your sequencer, or even procedurally generating your MIDI with some kind of script, another project I'm working on. In that case, it might actually be easier to work directly with values 0 through 15. So, although it sets it to spread automatically upon choosing velocity, you can always undo that afterwards if you want. Spread mode is available when pitch bend is assigned as well. To be clear, anything typed into these fields on the GenX screen is always in exact mode. The distribution mode only affects input received over MIDI. To remind you of this, anything typed in out of valid range is colored in this pink highlight. When I code the actual MIDI handler, most likely, when in exact mode, I'll have anything higher than the maximum just mapped down to the maximum value. The help text reflects this already, but it's not set in stone. Now, I hope all these usability concessions help to balance between the needs of somebody working at a MIDI keyboard and those of someone programming their music right in the sequencer or with a script. One last thing to show. When you start the program, you're on the Welcome page of the System tab, as I've shown. But if you go back to the System tab after leaving it, the program assumes you don't really need to see the Welcome screen again and instead takes you to the second Sys page, which is for channel assignments. On this page, we can assign any voice of any chip to any channel. Now, you can also make those assignments on any individual voice page as well, as I've shown, but I thought it would be convenient to have a central place to keep track of it all. As we move horizontally across the grid, the name of each column's voice appears near the top. I thought this was a nice way to handle the problem of displaying all those voice names when they won't all fit on the screen at once. Notice that the leftmost voice is actually the piezoelectric PC speaker. It doesn't have its own tab or voice page, since there are really no options to select for it, but you can send your MIDI notes there if you really want to. To assign a voice to a channel, get into the column for that voice and the row for the channel you want, hit enter, and it will light up. You can change the naming conventions of the channels, too. This is another convenience I've added. When you're coding MIDI data, there's no question as to what the names of the 16 MIDI channels are. They're 0 through F. Many sequencers, though, will render this on screen as 0 through 15, using decimal instead of hex. And some sequencers will refer to them as 1 through 16 instead. I find that annoying, but if you are using a sequencer that does that, then it would be even more annoying to have to remember that all your channels are one off between your sequencer and the GenX. So in this software, I give you the option to choose between these 3 naming conventions for the channels. You can do that from any voice page as well, as long as you're in the channel column. They are redisplayed in real time. To be clear, the value doesn't change, just the way it's displayed on the screen. Another convenience, by the way, is that from any voice page, you can hit the H key to jump to the channels page. One last thing on this page. When you assign more than one voice to the same channel, you're then dealing with polyphony. And a polyphony mode for that channel shows up on the right-hand side here. For example, let's assign all 6 soft SID voices to the same channel. The polyphony mode appears as soon as you assign more than one, and it is set to unison by default. This means that when you send a note on to this channel, all 6 of these voices, in this case, play that note in unison. This works best if you're combining more than one type of waveform to make a complex timbre, or maybe if you're using the SID's ring modulation capabilities. You can combine voices from different chips, too, for really interesting timbral combinations. The other 2 polyphony modes, by contrast, work well if you set all of the voices to the same waveform. Pressing P here changes the polyphony mode to polyphony steal. This means that you now have 6-voice polyphony, and if a 7th note is played, it shuts off or steals the first note. One more press of the P key gets you polyphony limit mode. Now if you have 6 notes playing and then add a 7th, instead of stealing the first one, the 7th simply will not sound until you release one of the others. In other words, you've reached the limit of the number of voices on this channel. Pressing P again cycles back to unison mode. Oh, and you can hit the H key again to jump back to whichever voice page you jumped here from. There is more work to be done. I need to tackle loading and saving for starters. You will be able to load and save presets for a given voice or any combination of voices, and the user will be able to decide the scope of any preset they save. In other words, how many and which voices it applies to. There's loading in the sense of loading presets from media, like the HD, floppy, or SD card, into RAM, and then there's loading as in making a certain preset in RAM the active one, i.e. loading it into the active registers for that chip. Ideally, you'll be able to do that second kind of load in the middle of a piece by sending MIDI patch change messages. Saving will be the same. You can save a preset to RAM and probably assign it a patch number for later recall. But then you can also save that onto one of the storage media. By the way, I will definitely need help understanding how to load and save from HD, floppy, or SD card. I just have to admit ignorance on this. I have no idea how that works on a retro system like this. I won't be working on that quite yet, but when that time does come, I apologize in advance for all the pesky questions I'll surely be asking in the Discord. Speaking of the Discord, someone there mentioned that I might also want to use MIDI system-exclusive messages. So those are useful for sending custom messages, but they're a little slower because even though they're actually variable in length, even at a minimum they contain a few more bytes than the standard messages. Even so, I might allow the user to send sysx messages to reassign parameters to MIDI controllers mid-piece, or maybe even rearrange the channel assignments, because it would be great to be able to change which chips you're using in the middle of a piece. But none of that is implemented yet. So there's a lot of quality of life features here that I hope can stay in. You know, the fact that you can assign different channels to different parameters on the same chip, or even across different chips. That's a few extra checks that have to be done during the MIDI handling, compared to if each voice were only one channel, and one channel was only that voice. That could streamline the MIDI handling process a bit, but at the cost of some flexibility. I hope I won't have to sacrifice that. The distribution modes, the various polyphony modes, even the fact that you can assign the same MIDI controller to control more than one thing. These all mean extra code that has to be gone through for each incoming MIDI message. Now, I think the GenX's 65816 at 14 MHz, or even at 12 MHz if that's how it works out, should be able to handle all of this without significant slowdown or latency. This is all being coded in 65816 assembly, by the way, and I am looking forward to the challenge of using all my 65816 efficiency techniques to get the MIDI handler to push data to chips as quickly as possible. Going forward, the plan is to get as many of these features as possible working on one chipset, the soft SIDs, and only then move on to supporting additional chips. But that could change. In the meantime, I'm going to take a break from this project for a bit, maybe until my GenX arrives, but we'll see. If anyone has any questions about the project, you can contact me on the Discord, or in the YouTube comments, I suppose. In any case, thank you all for your time.